The Barents Sea in October does not accommodate mistakes. The water at this latitude, 71 degrees north, 220 nautical miles northeast of Tromsø, transiting the approach corridor between the Nordkapp and the Svalbard archipelago, is 4 degrees Celsius at the surface and 2 degrees below the thermocline. With a 3 to 4 meters swell from the northwest and a sky that has been producing intermittent snow since 0200, the snow is not falling so much as moving horizontally. The northwest wind at 19 knots converts precipitation into a medium that is simultaneously rain and ice and wind-driven pellets, coating any exposed horizontal surface with a film of gray-white that makes footing uncertain and any topside work a careful exercise in weight distribution and grip. USS Forrest Sherman makes 18 knots on a northeasterly heading, transiting the Barents approach corridor after completing a surveillance operation against the Northern Fleet's exercise package that has been active in this area for the past 11 days. The tactical situation has been what the intelligence community calls a presence deterrence posture. The Northern Fleet has been watching the Sherman watching them, each side maintaining the specific professional distance that this kind of mutual observation requires. That posture changes at 3:19 a.m. The 53 to 65 K torpedo that the lead Russian SSN fires is a wake-homing system. It follows the ship's propeller wake backward toward the hull and detonates on contact or at a proximity setting. The Sherman's countermeasures deploy at 3:19:21 a.m., 4 seconds after the torpedo is detected by the hull-mounted sonar. The Nixie towed countermeasure creates a competing wake signature that the torpedo's guidance algorithm must discriminate against. The torpedo discriminates imperfectly. At 3:19:43 a.m., it detonates approximately 19 meters off the Sherman's port stern between the port propeller and the stern tube, at a depth of approximately 12 meters. The 300-kilogram warhead at 19 meters lateral distance and 12 meters depth produces a pressure wave that arrives at the port stern with sufficient intensity to produce structural effects without breaching the hull. No flooding, no fire, no engineering system failure immediately apparent. The port LM2500 gas turbine trips at 3:19:43 a.m. on its vibration protection system. The shockwave has exceeded the vibration threshold. But this is a recoverable protection trip, not a mechanical failure. The port shaft slows, and the ship yaws to port as the starboard shaft continues at operational RPM. At 3:19:46 a.m., 3 seconds after the detonation, the helmsman reports, "No rudder response. The wheel is turning. The ship is not turning." The officer of the deck calls out the no-helm situation. The chief engineer, in DC Central since the torpedo detection, reads the rudder system status at 3:19:48 a.m. Rudder position indicator reading 12 degrees starboard. Rudder not responding to helm command. Rudder hydraulic pressure normal. The hydraulic pressure is normal. The rudder is not moving. Normal hydraulic pressure with an unresponsive rudder indicates not a hydraulic failure, but a mechanical jam. The rudder itself, or the mechanical connection between the hydraulic actuator and the rudder stock, has jammed in the 12 degrees starboard position it held at the moment of the detonation. What the pressure wave from a 300-kilogram warhead at 19 meters does to a rudder stock and its associated mechanical components is a specific engineering phenomenon. The rudder stock on an Arleigh Burke-class destroyer is a 200-millimeter diameter steel shaft that passes through the bottom of the hull in a sealed bearing arrangement and connects to the rudder blade on its lower end and the hydraulic steering actuator on its upper end. The stock rotates within the bearing to turn the rudder. The torpedo's pressure wave arrived at 3:19:43 a.m. from a direction approximately perpendicular to the rudder stock's axis, applying a lateral impulse to the rudder blade and the lower portion of the rudder stock. The rudder blade, a large, flat steel surface approximately 4.2 meters tall and 2.6 meters chord, is an efficient pressure collector. The lateral impulse on the rudder blade at the moment the rudder was at 12 degrees starboard has imposed a bending moment on the rudder stock at its lower bearing that has forced the stock into contact with the bearing housing on its forward face at an angle that has created a friction jam. The stock can generate its normal rotational force through the hydraulic actuator. It cannot overcome the friction from the lateral bearing contact. The rudder is physically jammed in the bearing by the deformation that the pressure wave produced. The hydraulic system is fully functional. The rudder is mechanically locked. The commanding officer at 3:19:51 a.m. Asymmetric shaft power. Port shaft to 0, starboard shaft to flank. To induce a turn away from the submarine's last known bearing. The turn is slow. Asymmetric thrust from a single shaft produces a yawing moment that accumulates gradually at 18 knots. The ship is turning, but at approximately 1/3 the turn rate of a normally functioning rudder. And the turn rate cannot be increased above this without risking the starboard shaft at the current loading. The first problem is immediate and tactical. The submarine that fired this torpedo is still somewhere aft of the Sherman's current position, and a ship maneuvering only by asymmetric propulsion, which produces a curved track that is somewhat predictable, is a less effective defensive target than a ship with full rudder authority. The second problem is navigational. The Svalbard archipelago's southern shelf, where the seafloor rises to less than 60 meters, is 34 nautical miles to the northwest on the Sherman's current heading. A ship that can only turn slowly to the right has limited ability to avoid the shelf approach if the heading is not managed carefully. The third problem is the aft steering compartment. The Sherman's aft steering room is the space containing the manual hydraulic steering controls, the backup system that allows the ship to be steered from aft if the bridge helm control fails. The aft steering room is located at the ship's very stern, below the fantail deck, directly above the rudder stock. It is a small compartment, approximately 3 meters by 4 meters, accessible from the ship's interior through a double hatch arrangement via the aft machinery space. It contains the manual steering control valve, which can be operated by hand to apply hydraulic pressure directly to the rudder actuator, bypassing the bridge helm control entirely. But the manual steering control valve cannot override a mechanical jam in the rudder stock bearing. The valve applies hydraulic pressure to the actuator. The actuator tries to rotate the stock. The stock is jammed against the bearing. No amount of hydraulic pressure from the manual valve will move the rudder as long as the bearing jam persists. What can potentially free the bearing jam is a lateral impulse in the opposite direction to the one that caused it. A force applied to the rudder blade from the port side, pushing the stock back away from the forward bearing contact and restoring the stock's freedom of rotation within the bearing. This force can be provided by putting the ship in reverse thrust, which would drive water against the rudder blade from the aft direction and potentially shift the stock's contact point within the bearing, or by manually applying a lateral impulse to the rudder stock itself from inside the aft steering compartment, using the emergency mechanical rudder release tool, a 1.2-meter lever arm designed to be inserted into the rudder stock's manual drive socket and used to apply a torque to the stock that supplements the hydraulic actuator. The chief engineer identifies both options at 3:20:15 a.m. and calls the commanding officer, "Captain, engineering. The rudder is mechanically jammed at the lower bearing from the shockwave lateral load. The hydraulic system is functional, but cannot overcome the bearing contact. I have two options. Reverse thrust on the starboard shaft to introduce a counter-directional flow against the rudder blade. This may shift the bearing contact. Or entry into the aft steering compartment to apply the mechanical rudder release tool to shift the stock laterally. The aft steering room access is through the aft machinery space." The commanding officer: "What is the flooding status at aft?" "No flooding reported. The detonation was 19 meters lateral. No hull breach detected. But the aft steering compartment is at the stern. If there is any undiscovered structural damage near the stern tube, Entering the aft steering compartment puts someone in proximity to it. I assess the risk as acceptable given the flooding indicators, but I want you to know it. The commanding officer authorizes entry into the aft steering compartment at 3:20:29 a.m., simultaneous with an order for the starboard shaft to perform a brief 2-second reverse thrust pulse. The reverse thrust pulse is executed at 3:20:35 a.m. The starboard shaft reverses for 2 seconds, driving water against the rudder blade from the aft direction. The rudder position indicator does not change. The helm responds. Still, no rudder response. The reverse pulse did not free the bearing jam. The damage controlman assigned to the aft steering room entry begins moving at 3:20:31 a.m. He started moving when the commanding officer authorized entry before the reverse pulse. He is accompanied by a second damage controlman who will hold the safety line and the battle lantern at the access hatch while the first person enters the compartment. The route from DC Central to the aft steering compartment is aft along the 01 deck main passageway, through the aft machinery space watertight door, forward through the aft machinery space, and down through the double hatch access trunk to the aft steering compartment. The ship is at general quarters with condition zebra set, all watertight doors closed. So each door requires unlatching and relatching. The first damage controlman reaches the aft machinery space watertight door at 3:21:14 a.m., 43 seconds after moving. He unlatches it, passes through, and relatches it behind him. He reaches the aft steering room access hatch at 3:21:44 a.m. The aft steering room access hatch is a 60-centimeter circular scuttle in the aft machinery space deck. When he opens it and looks down, he sees what the structural assessment missed. The detonation at 19 meters lateral has produced a small but visible crack in the stern tube seal at the upper flange of the port shaft stern tube. A crack that is weeping water at a rate the engineering watch estimates at approximately 8 gallons per minute. The water is collecting in the aft steering compartment below the access scuttle. The aft steering compartment at 3:21:47 a.m. has approximately 12 centimeters of water on its deck. The compartment has been accumulating water from the stern tube seal leak since the detonation at 3:19:43 a.m., approximately 2 minutes of 8 gallon per minute inflow. The water is 4 degrees Celsius. The compartment is cold. The stern section of the ship, this close to the waterline, is poorly insulated from the exterior water temperature. The damage controlman can see the compartment interior. The manual steering control valve on the forward bulkhead. The emergency mechanical rudder release tool on its mount on the starboard bulkhead. The water covering the deck to a depth that reaches the lower step of the access ladder. He reports to DC Central at 3:21:52 a.m. Aft steering compartment has approximately 12 centimeters of water from what looks like a stern tube seal leak. Water is cold. The mechanical rudder release tool is on the starboard bulkhead, above the water level. The steering control valve is forward bulkhead, also above water. The rudder stock passes through the center of the compartment. I can see the stock and the actuator assembly above the water. The bearing housing is visible at deck level. I cannot fully assess the jam from here. The chief engineer responds at 3:21:59 a.m. Enter the compartment. Your task is to locate the manual drive socket on the rudder stock. It is on the port face of the stock, at approximately 1 meter above deck level. A 38mm hexagonal socket. Insert the release tool into the socket and apply a port directional torque. Push the handle of the tool toward starboard, which turns the stock to port. The jam is on the forward face of the lower bearing from a starboard lateral load. A port torque applied to the stock at the socket location should shift the contact point. You will feel resistance. The hydraulic actuator is holding the stock at 12 degrees starboard. Apply the torque against that resistance for approximately 15 seconds and release. I will monitor the rudder position indicator. The damage controlman enters the aft steering compartment at 3:22:07 a.m. The water comes up to above his boot tops, approximately 20 centimeters now. the flooding having continued for another 15 seconds. The water is 4 degrees Celsius. Through the boot leather, this temperature is felt as an immediate numbing cold that begins affecting manual dexterity within approximately 45 seconds of sustained contact. He needs to locate the manual drive socket, retrieve the release tool from the starboard bulkhead, insert it, and apply the torque before his hands lose the dexterity required to manage the tool accurately. He locates the rudder stock at 3:22:12 a.m., visible as a 200mm steel cylinder rising from the deck and connecting to the actuator assembly overhead. The port face socket is at 1 meter above deck as described. A 38mm hexagonal recess cast into the stock face, currently located on the port side because the stock is at 12 degrees starboard rotation. He retrieves the release tool from the starboard bulkhead at 3:22:19 a.m. A 1.2-meter steel lever arm with a 38mm hexagonal male head at one end and a T-handle at the other. He inserts the head into the socket at 3:22:26 a.m. The insertion is correct on the second attempt. The first attempt missed by 5 millimeters due to the combination of cold affecting tactile feedback and the difficulty of seeing the socket under the emergency lighting. He applies the torque at 3:22:31 a.m., pushing the T-handle towards starboard, which rotates the lever arm counterclockwise when viewed from above, applying a port directional torque to the rudder stock. The resistance is significant. The hydraulic actuator is maintaining approximately 2,200 pounds per square inch on the stock in the starboard rotation direction, and the tool's 1.2-meter lever arm at the socket radius of 100 millimeters produces a mechanical advantage that allows the damage controlman to overcome approximately 400 Newton meters of that resistance. He pushes. His hands are losing sensitivity from the cold air. The boots have kept his feet dry, but his hands have been exposed to the 4-degree compartment air since entry. He maintains the force for the 15 seconds the chief engineer specified. At 3:22:46 a.m., 15 seconds into the torque application, the rudder position indicator in DC Central shows a 0.3 degree movement from 12 degrees starboard to 11.7 degrees starboard, a fraction of a degree, but movement. The chief engineer calls the aft steering compartment. Movement detected. Maintain the torque. Do not release. I am monitoring. Continue the torque application. The damage controlman maintains the torque. At 3:22:51 a.m., the rudder position indicator shows 11.1 degrees. At 3:22:58 a.m., it shows 10.4 degrees. The stock is moving. The jam is releasing as the torque progressively shifts the stock's contact point within the bearing. At 3:23:09 a.m., the indicator shows 8.2 degrees, and the movement accelerates. The jam has released, and the hydraulic actuator, which has been trying to move the stock to port in response to the helm's commanded position, is now driving the stock freely. The chief engineer calls the aft steering compartment at 3:23:11 a.m. Rudder is free. Withdraw the tool and exit the compartment. He calls the bridge. Helm is responsive. Test the rudder. The helm reports at 3:23:19 a.m. Rudder responding normally. The commanding officer orders 5 degrees port, 10 degrees port, hard to port. The rudder moves smoothly through its full arc. Rudder authority restored at 3:23:19 a.m. The damage controlman exits the aft steering compartment at 3:23:24 a.m. 3 minutes and 40 seconds after entry. His hands are numb from the wrist to the fingertips. The combination of 4-degree air and the physical effort of maintaining the torque against the hydraulic actuator's resistance has produced the early stages of cold contact impairment. The medical officer who meets him at the aft machinery space entry assesses no frostbite, but significant cold-induced reduced dexterity that will require approximately 20 minutes of warming to restore. He is assessed as fit for duty following warming. The stern tube seal leak, the secondary damage from the detonation, is addressed by the repair party while the aft steering access hatch is still open. The seal crack is assessed as a temporary sealant repair candidate. The repair party completes the temporary seal at 3:47 a.m. The leak rate drops to 1.4 gallons per minute, within the P250's management capacity for the transit to Tromsø. The permanent repair requires dry dock work and is completed at Tromsø 11 days later. The aft steering compartment is pumped dry by 3:38 a.m. The water temperature on the compartment deck, measured by the repair party at entry, was 3 degrees Celsius. The flooding seawater had equilibrated with the compartment temperature, which was at 3 degrees from the combination of the hull exterior water temperature and the unheated stern section of the ship. The damage controlman's hands had been working in a 3-degree environment for 3 minutes and 30 seconds. The post-event engineering assessment identified the mechanical rudder jam as a failure mode not documented in the ship's damage control casualty procedures for torpedo near-miss events. The procedures addressed flooding from hull breach, propulsion loss from turbine trip, steering loss from hydraulic failure. They did not address steering loss from mechanical jam in the rudder stock bearing produced by a shockwave lateral load on the rudder blade. The emergency mechanical rudder release tool, which resolved the jam, is described in the hull maintenance documentation as a tool for manually overriding the hydraulic actuator in the event of actuator failure, not as a tool for releasing a bearing jam. Its use in this event was an application of the tool to a problem it was not specifically designed to solve, in a manner that was mechanically sound but not documented. The chief engineer was asked at the debrief how he knew the release tool would work on a bearing jam. He said he knew the tool's function, applying a torque to the rudder stock, and he knew the jam's cause. Lateral bearing contact from a shockwave impulse. He said a bearing contact jam produced by a lateral impulse can be released by applying a torque in the opposite direction of the impulse, which shifts the contact point circumferentially within the bearing housing and reduces the friction that is preventing rotation. He said the tool is designed to apply torque to the stock. Torque in the port direction was the mechanical intervention the situation required. The tool was the available instrument for applying port torque to the rudder stock. He said he did not know with certainty that it would work. He said the alternative, a mechanical rudder jam with no recovery attempt, was a ship that could only turn right in the Barents Sea with a submarine in the area. He was also asked about the flooding in the compartment. He said he assessed the 12-centimeter water level as a manageable working condition based on the flooding rate and the entry time. The compartment would not reach a dangerous water level during the time required for the tool operation. He said he communicated the flooding condition to the commanding officer before entry was authorized, and the commanding officer made the authorization with that information available to him. He said the damage controlman who made the entry knew the water was there before he descended. 153 to 65,000 torpedo detonated at 19 meters lateral and 12 meters depth at 3:19:43 a.m. Rudder jammed in 12 degrees starboard position by shockwave lateral load on rudder stock at lower bearing. No hull breach. Stern tube seal crack. 8 gallons per minute flooding into aft steering compartment. Port LM2500 trip on vibration protection. Asymmetric thrust maneuvering established. Starboard shaft reverse thrust pulse attempted at 3:20:35 a.m. Rudder not freed. Aft steering compartment entry authorized at 3:20:29 a.m. Entry team reached compartment at 3:22:07 a.m. Compartment water level 20 centimeters at entry. Emergency mechanical rudder release tool applied to rudder stock manual drive socket at 3:22:31 a.m. Port torque maintained for 42 seconds. Rudder movement detected at 3:22:46 a.m. Bearing jam released at 3:23:09 a.m. Rudder authority restored at 3:23:19 a.m. Entry team exited at 3:23:24 a.m. Stern tube seal temporary repair completed at 3:47 a.m. Leak rate reduced to 1.4 gallons per minute. Damage controlman. Cold-induced hand impairment. Assessed fit for duty after warming. Ship status, operational. The emergency mechanical rudder release tool that freed the rudder stock bearing at 3:23:09 a.m. on USS Forrest Sherman is a 1.2-meter steel lever arm with a 38mm hexagonal male head. It is mounted on a bracket on the starboard bulkhead of the aft steering compartment. It has been on that bracket since the ship was commissioned. It has a maintenance card that specifies an annual inspection. Confirm the bracket is secure. Confirm the tool head is undamaged. Confirm the socket fit on the rudder stock. It has passed every annual inspection. It was manufactured to specification. It was where it was supposed to be. The damage controlman who used it had never used it before. He had seen it on the bracket during the aft steering room familiarization walk that is part of the engineering qualification for DC qualified crew members. He knew what it was for because the familiarization checklist says what it is for. He did not know it would work on a shockwave-induced bearing jam because that application is not in any document. He knew the socket, he knew the insertion procedure, he knew the tool handle direction that corresponds to port rudder torque, because those things are in the aft steering equipment description on the familiarization checklist. He inserted it correctly on the second attempt. He held it for 42 seconds in 3-degree air with numb hands. The bearing released at 3:23:09 a.m. The ship turned left. The submarine did not fire again.